All right, good morning and welcome to this video solution on the topic of toroid. So, toroid is a very important topic for class 12th physics, and today we are doing a numerical from NCERT. So, let's read the question first. Essentially, a toroid produces a magnetic field. Just remember that. And we always need to find the magnetic field due to a toroid at different places. Okay. So if you see, there is an inner radius of toroid, which is this is the inner radius given to be 25 centimeter. Okay, this is the center. And the outer radius is 26 centimeter, which is this. Okay. 26 centimeter. So a toroid has 3,500 turns. So you might have seen a toroid and the loops it has. So a toroid looks like donuts, right? If you have ever tried donuts, it looks like that. Remember, a toroid has to be very tightly wound. A loosely wound uh, toroid is not a good approximation when it comes to the mathematics of toroid. So this is just to give you an idea of shape of the toroid. Now let's talk about the toroid has how many turns? 3,500 turns, right? So we will show the turns also. If the current in the wire is 11 ampere, what is the magnetic field outside the toroid, inside the toroid, and in the empty space surrounded by the toroid? So let's talk about the current. Okay, the current is I told you the it is tightly wound and there are a lot of loops in a toroid. So the way current is shown in a cross section diagram is this. So this represents, okay, for every cross I will draw for every. So this is the loop, the current loop which is covering the toroid. So you might have seen a solenoid. A solenoid is like this, right? So if you pick up a solenoid like this and you make it circular, right? You make it circular. This is what it becomes a toroid. Okay, it becomes a toroid, and obviously you will have incoming current and outgoing current in it. So let's say this is the incoming current and this is the outgoing. So this is a toroid, and if you notice this, these are the loops which I am drawing now. In the cross section, they are shown as dots and cross, but these are the loops being referred to. Okay. So a solenoid is converted into a circle shaped figure. It becomes a toroid. Now, if you notice, I am drawing these loops. So I have drawn two loops, third loop. Similarly, you have 3,500 loops. So we will not draw 3,500 loops. The current is 11 amperes. Now let's talk about the places. So we have to, so I told you it produces magnetic field. Okay. So let's say we do have this, lot of 3,500 uh, loops which are there, and they cover the whole toroid, which looks like a donut. Okay, and I'm not drawing all, but this is very uniform. I have just drawn it like this. The Don't worry about this spacing. This spacing is equal. Okay, my diagram is not the perfect diagram, so these spacings are uniform. It is uniformly wound, and a corresponding dot is also there. Now, when we draw cross, okay, cross is always the current which is flowing here in the loop. The current for a cross is going inside the plane, going inside the plane. Okay, so the current is going inside the plane. And when you show a dot, that current is coming out of the plane, coming out of the plane. Okay, so this dot is the current coming out of the plane, and there is a loop, right? So a loop is like this. Okay, and if it is going inside the plane, it is a cross. If it is coming out of the plane, it is a dot. So that is clear in your mind, right? How the diagram is to be drawn. Now let's focus on the next part of it. So I'm just, for the sake of completion, I'm just drawing some dots to represent the coming out of the plane, and then correspondingly we will just draw some. So this diagram will look slightly better than it is right now. At least the toroid will look complete. That is the idea. I know it's a bit time wasting, but let's let's just make it, okay? And don't worry about the spacing. Spacing is equal. I am drawing with my rough hands, and therefore the spacing looks like that. So don't take too much tension because of that. Okay, now other part is, the current is known to us. So I is equal to 11 amperes. We know the radius one is, inner radius is 25 centimeter. R2 is equal to 26 centimeter. Okay. So, and the question is, we have to find out the current outside the toroid. So if you see the word outside the toroid, okay, outside the toroid means what? Here. Okay. So what we do, I'm drawing another circle with my, so this is the Amperian, you know, it solving a toroid and solenoid both use Ampere circuital law. You must know how to apply Ampere circuital law. So essentially, the question is, find the current sorry, the magnetic field outside the toroid. So this is where it is asking you to calculate the magnetic field. The second is, find the uh, inside the core of the toroid. Okay, so inside the core of the toroid means what? So let's say this is the core of the toroid. So we are talking about the core of the toroid. So inside the core means this. The space between external radius and the internal radius constitutes. And I'll tell you what this circle is, but right now I'm just showing you the space of the. Okay. And now let's also talk about the empty space surrounded by the toroid. So this is the empty space which is surrounded by the toroid. Okay, this is what it is. Now let's talk about the. So we have three areas, right? This is completely outside the toroid. This is outside the toroid. Okay, this one, which is the empty space surrounded by the toroid. This is the empty space surrounded by the toroid. Okay, this is the empty space surrounded by, and then of course, when they say inside the core, so this is the inside the core. So you must be able to mark the areas first. Okay, just remember that. I hope the diagram is clear to you. I am giving you a lot of explanation which no channel will give. If you're liking these videos and you want me to continue, please do subscribe to my channel so that at least I can impact 1 million student, and sitting at the comfort of your, you know, home, you are learning physics which you will not even learn in your classroom, application, portal, website. This is the power of my YouTube channel, where you're learning the concept sitting at the home free of cost. Okay, now let's move forward on this topic. So let's talk about uh, how do you find the magnetic field and what is the logic. I told you the logic is for these questions on toroid. Okay, so let's talk about the first one. Okay, and I will tell you the circles I have drawn. What are these circles? Okay, the first thing you must remember, they are based on Ampere circuital law. This is one. I hope you know the Ampere circuital law. Second, we will write it now. Second, you must remember is that the toroid is a special figure, and our focus is always in Ampere circuital law on the total enclosed current. Total enclosed current is always our focus, right? When we talk about Amperian loop, and you can watch my video on Ampere circuital law also. It is available. Okay, this is one Ampere circuital law, then total enclosed current. The right hand rule, right hand rule is used for finding the direction of magnetic field, for finding the direction of magnetic field, direction of B. Okay, so if you notice this question, in this question there is absolutely no mention of the the direction. They just want us to calculate the magnitude, but I will help you understand how do you find the direction of the magnetic field also. So far, I am sure you're good. You understand what's happening. We always worry about the total enclosed current, and we have to hold the right hand in such a way that, for example, this is your toroid, right? So this is your toroid. So you have to hold your right hand in such a way that the coils of the toroid, which are these coils. For example, I will just enlarge this, right? I will just enlarge the toroid for you. It's not a perfect toroid, but your hand will finally have a situation where, your thumb will go up in this direction and your fingers are here. Your five fingers will have these curled in the hand. Okay, so right hand, so this is your right hand, this is your thumb, so to say. Okay, this is your thumb, I will say. So remember, when a circular coil is enclosed, so when a circular coil is available to you and you try to apply the right hand rule, the direction of magnetic field is tangential. Okay, so for a circular loop, when you apply the right hand rule, hold the loop in your hand so that the current is enclosed. The direction of the current, sorry, the magnetic field is tangential. So for every loop, you will have a tangential direction of the magnetic field. And I will tell you the significance of this. I am not teaching you how to apply right hand rule. For that, watch my video for Ampere circuital law. It is lot of detail is available which explains it. I think our focus here is just to solve this numerical, but I'm giving you tips so that it becomes easy for you to solve any numerical which you see on toroid. Right now, you will never forget how to solve a toroid numerical. All right, so let's talk about solving this numerical. First, let us focus our attention to the middle part of it. Okay, so let me show you the middle part, when I say middle part, I mean I will start from, okay, let's start from, the sequence which is given in the question. First, they want us to calculate outside the toroid. So let's say I had drawn this, if you remember, when we started, I drew a red color circle, right? So to show you the region which is outside the toroid. What constitutes outside the toroid? So this is the outside the toroid. This is drawn outside the toroid. Okay, this is where we need to find the magnetic field. So if you think in terms of the outside the toroid, see what is happening. We have to apply the Ampere circuital law. Okay, now Ampere circuital law you can apply. Now first focus on the directions or the current enclosed. So first of all, if you notice outside, which is the bigger red circle, this red circle is being referred to. You have some current which is this current, right? This current which is going inside the plane, and associated with the same current is a current which is going outside the plane. So this is outside the plane, this is inside the plane. We already discussed the significance of cross and a dot, right? So if you notice outside this particular situation, the net current which is enclosed is how much? Zero, because the sum of the current which is going inside and the current which is going outside, which is a dot, is zero, right? So let's write the Ampere circuital law and think about it. Okay, so how do we write this? We know that Ampere circuital law is BDL. It's a circle, so B into 2 pi r, for example, right, is equal to mu naught into 0, because you have no current, right? So A, when you say outside the toroid, the total current enclosed, as per the law, it should be B 2 pi r is equal to mu naught n I, right? N is the number of loops, I is the current, but total current enclosed is zero, because in outside current coming inside and coming, the current which is going inside and coming outside through the plane of the paper is zero. So net I enclosed is zero, right? So I enclosed is zero, and therefore there is absolutely no magnetic field outside the toroid. Okay, so there is no magnetic field outside the toroid. This is answer number one. Okay, I hope this is clear. What we discussed was the region number this. Okay, so this is the first region outside the toroid. Now let's talk about the second one, inside the core of the toroid. So inside the core of the toroid means what? Inside the core of the toroid means the region number 2 here, right? If you look into this region very carefully, this region only includes this current. Can you see this? The current which is going outside the plane, coming out. So I'm just re-highlighting it with the pink color. So this is the current being referred to. This current is not to be included. We always include the current which is enclosed by the Amperian loop, right? So if you hold uh, each of the current here with the right hand, right, you will find that there is no cancelling current. But in the case of outside, inside and outside were cancelling. But in the case of situation number 2, which we have just showing as this situation, the current is only this current being referred to, which I'm again highlighting, which is coming outside the plane of the paper. So we are referring to this particular current. I hope this is making sense to you. Okay, so the situation number 2, which we are referring to, has a current enclosed. So let me just write the formula for this, and this is situation number 2 inside the core of the toroid B. So B dl integral is equal to mu naught. How many times you will apply right hand rule for every current dot? It's a dot because the current is coming out. You will apply it, and therefore you will write it as mu into n into I, right? So this is 3500 we are already given. This is 11 ampere, and we know what is the radius of the inner one, right? So it will become B into 2 pi into R, which is 25 by 100 is equal to mu naught into 3500 into I. And how much is I? I is essentially given to be 11 amperes. With this, you can find the B. I hope this made sense, right? We are able to find the B also with the help of this rule. So magnetic field you can find, calculate this, you will get the answer of the magnetic field. This is in meters, this is number of turns, this is 11 amperes, this is the permeability of the medium. Okay, let's talk about which is the core of the, right? So for it's a, I'm assuming it's air because nothing is given to us. It's a, yeah, so let's say there is nothing given to us, and in the empty space, okay, the last part is in the empty space surrounded by the toroid, right? So we have to find it in the empty space. Empty space surrounded by the toroid is the center of the toroid. So I will just highlight that region for you when it says the empty region surrounded by the toroid. So this is the region being referred to. Okay, this is the region being referred to. This is the empty space, right? The toroid is surrounding this, right? If you notice this, and if I take any Amperian loop in this, you know, and inside, for example, I take this Amperian loop, how much current is enclosed? There is absolutely no current inside this, in the region surrounded by the toroid. So here again, the answer is in the C part. If you notice the C part, answer is what? That there is no current, there is no current inside the empty region surrounded by the, there is no current inside the empty region surrounded by the toroid. This is very important, okay, that you understand this. So therefore the magnetic field, which is BDL, is equal to mu naught and the total current I enclosed. When you have no current present, you know, you just write it as 0. So mu naught into 0. So B is equal to 0. So you see outside the toroid and inside the space surrounded by the toroid, the answer is 0. Whereas in the space which is between the two, the core of the toroid, you still have some magnetic field available to you, right? So this is one. Okay, I hope this is clear. Now let's talk about the direction, which you have to understand very carefully and memorize this so that you have no confusion in your exam. See, if you get a situation in which the current going inside the coil, okay, is a cross on the outer radius like this. Okay, this is the cross and this is the dot which is coming outside. The magnetic field which you got in the core will be anti-clockwise. Okay, so the I told you I'm drawing this is the magnetic field which is drawn like this is anti-clockwise. But if you reverse the situation, which means you put a this is you inverse the direction of the current, which means this is going out, this is coming outside, and now this from here it is going inside. So this is going inside now and this is coming outside. You reverse the direction, the magnetic field will become just the reverse, it will become clockwise now. So the circle which I have drawn, this circle is the magnetic field, okay, because it is tangent to each of the circular loop. So when you join all the tangents, what you get is a circular magnetic field inside the core of a toroid. So remember this, if you invert it, you will get a clockwise magnetic field which is circular. So the shape of the magnetic field inside the toroid, the core of the toroid, is anti-clockwise, right? I hope you will be able to memorize, right? Listen to this video very carefully. If the cross is seen to you, the cross represents the current which is going inside and the dot represents which is current coming outside the plane of the paper. And for this arrangement, the direction of magnetic field, the circular magnetic field in the core, is anti-clockwise. Inverse the current, the magnetic field become clockwise, circular again. Okay, so right hand rule should be understood very well. Then Ampere circuital law should be clear to you, the formula should be very clear to you. So I hope you will never forget how to solve a toroid question when it comes in your examination. Watch my complete playlist on magnetic effects, magnetism, and you will get some fantastic questions pertaining to this topic. Thank you very much for your time and wait for my next video. reflected rays. Thank you.